I think we can start. I will make a short introduction and pass you the floor. Does it sound good?
Sounds good.
Okay. Let's start. Hello, everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Today we have Peter Nugent from the University of California, Berkeley, talking about the LICEA Schmidt Southern Survey. Peter, thank you very much for being with us today. The floor is yours.
All right, thank you. So now that this is all tested, we'll get this fired up, and here we go. Um, this is a relatively new project conceived of and put together entirely during the time of COVID, which is a shame, but it was too good of an idea not to do, and so there was a lot of motivation behind putting it together. And the synopsis of it is in my subtitle here: a shallow southern high cadence optical survey to complement the Rubin Observatory. And this, at the end of the day, is what motivated us to do this. So an overview. I am basically going to give you the who, what, where, when, how, and why for all of this, with a concentration, most of it on why. First, I'll motivate how this idea came about, and it basically started during my time running the Palomar Transient Factory survey and doing the processing at NERSC. Once we realized we could get on top of that survey and basically process things in real time, and that we could scale it by a factor of 2, the thought came to us, well, why not try doing this in other places and sort of increasing the reach. And so the pipeline that I wrote eventually wound up being used by a couple other surveys. One of them was the Palomar Quest survey, which then had moved down to LICEA when PTF took over and became the LICEA Quest survey. And some people have taken it for, and certainly the ideas down in Chile, doing a survey with the dark energy camera, as well as folks at Subaru and their camera. And so, then you start looking around for telescopes, and, we had this idea in the back of our head, and these people are using it, and it's working, and they have their pipelines running at NERSC or at their own institution. And then, we were moving from PTF over to ZTF. And so we were taking the old camera out, and I asked Sri Kulkarni, well, why don't you think about moving that camera down to the south? There are a couple of Schmidts down there, and one could run a survey that covered the entire sky. And he looked at it and he waffled on it a bit, and I think the hands were tied sort of with ZTF and trying to get all of that to come together. So he didn't want to overextend himself, but that thought was in the back of my head that basically it wouldn't be hard from the pipeline side of things to do another survey. I also had a lot of ideas on what was going into ZTF and how to make things better. And that the idea of covering the whole sky is beneficial. And so that was the seed of the idea that, came about. And if you look at it, there are basically only a few places where you can do wide field optical surveys, shallow ones. And I'll get to that in a second. But, you know, why would you consider a shallow optical survey at a time when you have ZTF in the north? But if you're down in the south, you'd overlap with projects like the Rubin Observatory, but also there's DECAM and BlackGem. And the first thing that I think any of us who have been thinking about Rubin and where it fits in is that the design of the large survey of space and time, LSST, is not optimal for many transients. And so the reach of the experiment is impressive, but most science cases are looking at high precision photometry or astrometry over long periods of time for, you know, the bright end of the transients, variable stars, hyperactive motion. While on the fainter end, the focus is at higher redshifts, fainter objects with slower evolution. So type 1a supernova for cosmology, you know, or even things like NEOs and KBOs. And there, what you need to do is pave across the entire sky. The Rubin Observatory suffers from the fact that not all volumes are created equally. And this really gets into the follow-up. The majority of your detections, by definition, are going to be at the magnitude limit of your telescope. And that's 24th magnitude. And you need an 8 to 10 meter class telescope even to get a spectrum for that transient. And so that's not ideal because there are only so many of them available. And even when the 20 and 30 meter class telescopes come online, there's just not enough time to follow the sheer volume of discoveries that the Rubin Observatory will be putting out. So you can also turn that around on its head and note that while the Rubin Observatory gets to 24th magnitude, it also saturates at 16th magnitude. And if you're a transient on top of a bright galaxy, it's even less than that because the galaxy itself will start saturating once you put a transient on top of it as well. And so that knocks out a huge chunk of the local universe as well. And then finally, it's really obvious today, I would say, is that one survey is not the path forward for transient astrophysics. Two or more overlapping surveys are really, you know, what people are doing now to make it cutting edge. And I would say PTF and ZTF sort of highlighted this with the SED machine that they had, you know, automatic spectroscopic follow-up, low resolution, albeit to get the brighter end of the transients, but they still found a ton of transients for which there's no information, not even information on the host galaxy. But we're now starting to get other surveys that are coming in. There's DESI, there's Foremost Tides, LSST will be there. You'll have WFirst at some point. DES did an amazing job down in the south, and even the DECAL survey, which was used to get the target selection for DESI, did a great job in the north and covering sort of 14,000 square degrees of extragalactic sky above the deck of -30. And so using that information is really valuable, and leveraging it and leveraging these future surveys. So keep this in mind. We're going to come back to it and sort of highlight each of these. But with this in mind, we can sort of quickly go to the where and when questions. And there are only two options, actually. You need a wide field camera. And the only two true options are the CTIO half meter Schmidt and the ESA 1 meter Schmidt at LIneA. And here we have a plot of the étendue of basically all the survey telescopes telescopes that are out there in both the north and the south. So field of view and square degrees versus light collecting area. And what I sort of want to highlight, and I don't, well, maybe you can see it, is where ZTF is, sort of in the center of the plot there, and where LSST is, you know, down into the right, and that's always a you know, a nice spot to be. But then you have these other surveys that are going on right now. Atlas, previously you had LIneA Quest, which is sort of in the middle below ZTF. You have Black Gem, which is just getting on Sky. And then you have these other surveys, HatPi and TESS, which have much smaller light collecting areas, but are quite a large field of view. And so the thought is, where can you have a lot of impact? And the LIneA Schmidt has the biggest impact. And if you retrofit it, which I'll show you in a second, you can actually jack it up to where it's about half the size of ZTF. And in addition to which, you have a whole bunch of things going on, so, you know, such as LSST's survey going on the Rubin. You have DESI starting off now, and you have the gravitational wave folks who are going to have 04 starting in 2022. So you'd really like to be on Sky by 2022 to be ready to take advantage of all of these potential synergistic activities. And so looking at this, we said, okay, we could refit the LIneA Schmidt camera with DES CCDs to cover the entire focal plane, which would be 20 square degrees, which sort of gets us to about a half a ZTF. This is, none of it would be vignetted, be ready to go. And you could imagine, for expediency's sake and lack of moving parts, just having a shutter and no filter wheel, just it's fixed filters. So you'd have a filter tray you could slide in. You're not changing it that often. And you could imagine setting it up with 1 or 2 or 4 filters of your choice and just running the survey that way for several months. So I'll describe where the CCDs come from later, but now I'll sort of step into the why about this and the sort of scientific motivation, you know. So why consider a survey? So once again, we have this plot of étendue, and I'd mentioned before, LSST in the south saturates at 16th magnitude. You have a survey like HatPi, which is on the bright end of things, right? It's going from, you know, magnitude -2, -4, down to 14th magnitude. And so you could imagine if you were somewhere in the middle, bridging the gap between those so that you literally cover the entire sky between, you know, the brightest stars on the sky down to 24th magnitude with LSST. What you sort of want to get out of a survey, in my mind, is that the volume should be large enough to provide nightly discoveries. And with them, there need to be a large enough number to discover some exotic transients, you know, sort of, that's sort of the sex cells in the transient world, finding something that nobody has seen before. But it shouldn't be so deep, like LSST's survey on the Rubin, to stretch your follow-up resources. And there, they're going to give up on 95% of the things they discover. So we'd sort of be like to be the opposite of the Rubin transient discoveries and try to get a spectrum of everything that goes bump in the night. So that's sort of the volume where we wanted to fit and why LIneA was a good match. The next part is the cadence, you know, and so these are the proposed cadences for the large survey space and time. And this one on the left is the Kraken 2026 cadence, and the one on the right is one proposed by Lachner et al., modification on this. And what we have here is a type 1a supernova at intermediate redshift, something that they're going to find hundreds of thousands of during Rubin's survey. And they're fit with the standard SALT-2 model. And what you can see is that you're getting data in the first survey, you basically repeat in a filter like every 16 days or something like that. In the second case, you sort of increased your survey in GR and I during dark gray time. And you're getting points about every 8 days or so, some with larger gaps than others. This is about, and it doesn't matter. You could imagine, even if you're a transient aficionado like myself, you could imagine taking over Rubin and just doing a GRIZ survey, and at best you're going to come back every week in the same filter. That's about all you can do, and still survey a decent chunk of the sky. And so it's not optimal. And so if we would like to find something which evolve quickly, and we want to be able to get on it and get a spectrum, and we want to know that nothing was there the night before, you have to have a much higher cadence, like nightly cadence or every other night. In addition to which, colors at the same time are incredibly important. If you get a G-band point this night and an I-band point 4 nights later, and you see it's red, well, was it red 4 nights earlier, or was it strongly evolving from the blue to the red? And this is important information. We know that at least from the one example we have and the theoretical models, that the binary neutron star mergers are red events just due to the opacity and the line blanketing in the ultraviolet through the midway of the optical. But we also know supernova are very hot and blue in the beginning, especially the core collapse supernova, and then they cool down. And so getting colors immediately tells you something about the priority and your ability to trigger on it. Do you want to trigger on something because it's hot and blue and young? And so that's why we needed to think about that as well. So for the gravitational wave follow-up, you get a trigger on the sky, you have something like 100 square degree uncertainty box if you're lucky, and you want to trigger everything on the planet and in space, UV from space, IR follow-up on your 8 to 10 meter class telescopes. You want to do all of this and as quickly as possible. But when you go out and you survey 100 square degrees of sky, just randomly, you're going to find a lot of transients. And I recall when the neutron star merger in 2017 occurred, they had a prioritized list of something like 200 galaxies that they wanted to go through that were sort of in the right redshift range. And these were known galaxies. And these were galaxies with redshifts that they were going to target. There were many more galaxies within that redshift there. They just didn't know what they are. So that was their list. And people started going through the list. And the team that discovered it, they picked the right galaxy the first time. There were other teams that was the third galaxy on their list. And, it's a mess. Now, if you push this out to 200 megaparsecs instead of the 40 megaparsecs, that list grows exponentially. And this becomes untenable. So what do you need to do to look at the transients and cull them? You need to know, was there anything there the night before? And that's why a nightly cadence over a large fraction of the sky is really useful. And so being able to discard potentially uninteresting things is is very important, but also color is important. And here you can see a plot of the optical through IR of that GW event, along with several other short, hard gamma ray bursts. And you can see these are very red. So being able to get something blue and something red simultaneously and know that it's young and seeing that it's red would lean you into favoring that target for additional follow-up. And so this is a primary motivation of the survey, being able to cover the sky on a nightly or every other night basis, a good chunk of it being able to respond quickly to transient events, pave over the sky in multiple colors, and use all the information at hand to understand, is this a good object or is it not? Now, there are a lot of other interesting things that you can do if you have a good cadence, and a couple of the ones that the supernova community are very interested in is looking for both pre and post outbursts for supernova. So here's an example of a pre-outburst. This was done by stacking data in the Palomar Transient Factory in bins of a week. So they would take the 14 to 15 images taken during weeks, stack them up. And for this supernova, which they noticed exploded there, marked on day 0 on the plot, around 20.5 magnitude, that if you went back, you could see previous outbursts. And in fact, they went back for this one and they saw outbursts a year earlier and 2 years earlier. They think, a possible explanation for this is super Eddington fusion luminosities slightly prior to core collapse, where you just slop off a decent amount of mass, something on the order of a few hundredths to maybe even as much as a tenth of a solar mass at 1 to 2,000 kilometers a second. And just these puffs create something in the absolute magnitude range of minus 15 to 14. Now, if Rubin comes along, it might see a few of these things. It's easily detectable in the nearby universe. That's only 21st magnitude. Rubin, could have even seen prior activity before that. And then it would see this supernova, but it wouldn't catch it immediately, and it would fall a poor light curve afterwards. It wouldn't be so characterized so well. And who knows if anybody would bother getting a spectrum of it. But if you combine what Rubin was doing with a survey where you're doing it every night and you're getting out to 200 megaparsecs where you can discover these supernova, then all of a sudden this becomes something you can do in a statistical sense and say, how many core collapse supernova exhibit signs of this before they go supernova? Another one are the post-outbursts, and these have now been seen in a handful of supernova, typically 2 classes, a 2Ns and a type 1A supernova that becomes a 2N. So you're going from some sort of thermonuclear explosion into something where you slam into a wall of hydrogen, and that's what then powers the supernova discovery. And so what we see here is a UV survey that was done with HST, where they did a snapshot survey and they went back and looked at a variety of supernova, both 1As and 2Ns. And the 2 discoveries are on top there. You see 2015 CP right in the center, and you see Assassin 15 OG. CP was a type 1A supernova. And so this was startling to see. This was 2 years later. They saw this interaction, and Assassin 15 OG was a 2N, and 2Ns have been seen to exhibit incredibly long light curves over multiple years due to constantly running into new circumstellar material. When spectra were taken at VLT and Keck, what you can see is a strong H-alpha line. The cool thing about this is that you could imagine that a survey done, a shallow survey that finds a trove of type 1a supernova. And if you look at, say, ZTF, in their 3 years, I think they discovered about 1,000 type 1as that they spectroscopically identified each year. And then you could use Rubin to probe, and this H-alpha line, while it would have been impossible to have seen in PTF or ZTF, is trivial for Rubin. It'd be much brighter than 24th magnitude. So you wouldn't have to go to space, which is what we did to see the UV part of it, but you could actually do this entire thing in the optical. And this is really neat because it highlights what we think is another potential path to making a 1A, type 1A supernova, which is a binary system, white dwarf with a main sequence or some sort of red giant or subgiant with hydrogen in its atmosphere that's accreting, burning to helium, and exhibiting nova explosions. And so the nova sort of clears out all of the mass loss going on in, say, that red giant and pushes it out to a decent distance. And this might have occurred 100 years before, and the nova velocities are like 1,000 kilometers a second. And then you have a type 1a supernova explosion. And for the first year, it expands in a vacuum because that nova over the previous 100 years cleared everything out. But then a year later, because it's traveling at 30,000 kilometers a second, it slams into this shell that the nova created and lights up. And so that's something that this survey can do. And once again, do it in a statistical sense. Other interesting things that can be done is getting on something incredibly early. So this is something that we did in PTF, and ZTF did it as well. Here's a timeline of this is a type 2 supernova, and you can see the first 2 data points that were taken right after a whole bunch of non-detections, and then triggering Keck right afterwards. It was done. You can see the plot there, hours where you had the first image. That candidate was loaded into the database. You had the second image that issued an alert because it was now confirmed. And then just an hour and a half later, a Keck spectrum was taken. And then Swift was triggered just a couple hours after the Keck. And then EVLA was triggered just a few hours after that. And then we started follow up with Las Cumbres Observatory. So what you want to do here is be able to trigger spectroscopy during the night, or at least within the next night, in order to effectively bring to bear these types of resources on a very young transient. And why do you want to study young transients, young supernova in particular? Because there's so much information there about the progenitor system and what's going on for those early observations. That it's key to really getting at the underlying explosion mechanism. Here's one example of it. It's called flash spectroscopy. This is sort of pioneered by Avishai Gal-Yam. This is an example of 2013 CU, taken about 15 and a half hours, the spectrum after explosion. And what you have, and this is a little cartoon plot down here, is the supernova is sort of embedded in this environment where you have mass loss coming off of the star. And here you have it compared to a bunch of Wolf-Rayet stars. So our very first spectrum there is compared to a bunch of Wolf-Rayet stars. And it's a Wolf-Rayet spectrum. And why? Because basically the supernova is just a hot background acting like a light that reflects this medium that the Wolf ray is in, and just amplifies the Wolf ray spectrum. But then you go to the next night, and what you see here is now the supernova has started to expand, and now the supernova is becoming the spectrum. First, it was just a hot black body, lighting up the background. Now you've got some of the supernova and some of the Wolf ray star, and you can see the lines are incredibly weak compared to the original lines. And even just a day or two later, they're gone. All those lines are gone. And then a few days after that, you see a regular core collapse supernova. So you missed that entire thing where you got to actually see a hint of the progenitor system. If you had a cadence like LSST, you're more likely than not to just get a spectrum with something and it looks like this, and you've missed that entire early evolution that took place in just the first few days. So that's another motivating reason. Another great reason for having a good cadence is poorly localized gamma ray bursts can be searched for over large chunks of the sky and monitored for their quick evolution. Here's an example from Singer et al., IPTF 13BXL. They did a search in 71 square degrees. You can see they were very lucky. They were able to catch this one. It was confirmed with radio and spectroscopy. But you can see they plowed over the error circle as much as they could. And then they had an IPN localization from all the other satellites that homed in on a tight swath. And there they found it just outside the lat error, 1 sigma error circle. And this allows you to then study, the poorly localized ones are off axis at some level. So it gives you the ability to follow these things up. The thing is, if you go through and search 71 square degrees, just like for the neutron star mergers and the gravitational wave follow-up, unless you know what was going on there the night before, you're going to have a lot of things that you need to sift through in order to figure out what's going on. Another example here, just outside, just within the 1 sigma error circle, another poorly localized GRB at a redshift of 1.87. And without knowledge of what was going on the night before, there were 30,000 variable objects within that error circle. And so, just a huge thing to sift through unless you know what's going on. So now that you got an idea of the volume we're interested in, the cadence we're interested in, now it becomes a big thing. Who are we going to feed this to, and how are we going to follow this up? Because my big thing is not the survey itself, but it's about the follow-up. The survey is a means to an end, and the end is the follow-up. And so the best follow-up in our mind is from the public. So 90% of the survey will be streamed to the 3 major brokers in real time, Antares, LIneA, and Alersi. We would like, and we've gotten commitment from one of them, but I think the others will fall in line, to fold in the Rubin data stream to maximize the science. So if Rubin hit that chunk of the sky in G-band to 24th magnitude the night before, and then we see something that night, that becomes part of the alert stream and adds tremendous value to the discovery. And then we're also going to work hard to provide added value for stacks of data where we sum up a whole week's worth to push fainter and to make sure nothing was going on there before. Other follow-up, we will have DESI and tides foremost. And just as ZTF is to LS4, 40 square degrees to 20 square degrees, north and south. DESI is to tides foremost. DESI, 8 square degrees, 5,000 fibers, a 4-meter telescope in the north. Tides foremost is 2,500 fibers, 4-meter telescope, 4 square degrees in the south. These folks won't necessarily be able to follow things in real time, but they will be able to, very importantly, get the host galaxies of almost everything that we observe. And that is huge, because even if we don't get a spectrum, we can maximize on that. The big push, though, will be the Son of X shooter, SOX. SOX is going to be starting in 2022. And it was designed to follow up and not only discover and spectroscopically identify nearby transients, but to follow them up as well. And so we see SOX as a major consumer of what we're doing, and a huge amount of added value combined with LSST. But we're not limited to that. We're also have our eyes as a collaboration on the CTIO 1.5 meter and the 1.3 meter telescopes. For the 1.5 meter, there's a Cosmos spectrograph, which is sitting right now inside the 4 meter, doing nothing while DE-CAM basically gets all the time. On the 4 meter. And so discussions are underway with CTIO about moving that spectrograph and refitting it with an R of 400 GRISM to take slit spectroscopy of discoveries that we find with LS4. The 1.3 meter, the thought would be to do something with retrofitting AndyCam to place a new IR Mercatel in there, so that we would have IR follow-up capabilities for our brighter targets. Our survey design. So these are some of my thoughts on how to design a survey properly. The first is a warning. Don't design a survey to find certain things. You will find what you were searching for. That's if you want to find something new, you need to search for everything. So combining the power of multiple observatories, keeping our cadence flexible, that's something we need to think about. Another great lesson learned is the computing science folks have to be interested in the astronomy, and the astronomers need to be interested in and respect the CS personnel. All major discoveries from here on out are going to be enabled by computing in one way or the other. And so we need to really hone the integration of these two fields together to optimize this. We should work constantly to improve our pipelines and our science. We need to be able to drop old bad science, computing science, and bring in new and improved science and computing science. So things need to be modular, they need to be flexible, and you need to really be able to step back and critically evaluate ourselves. Speed is very important. You know, we would like to be able to trigger telescopes within minutes of a discovery. And so optimizing this turnaround, it completely opens up new discovery space. That's really important. And keeping track of everything we do, decisions on what we decide to trigger spectroscopic resources on, why we set the cadence, how long we ran that cadence. You need that for doing anything like rate surveys and truly understanding your science. So to that end, we're going to do something similar to what we did with the ZTF Uniform Depth Survey. Here is where we targeted. We targeted in the DECAL's DR8 footprint. This ran from end of December last year through May of this year. We targeted that chunk of sky where we had nice photometric redshifts for everything. And we just laid down a really nice constant survey in G, R, and I. So something like that is great for a whole bunch of science. And we're going to be working this pipeline at NERSC, which I'll describe in just a second, and also using a tool that Josh Bloom has developed called Sky Portal with a lot of great Python engineers, which allows us to keep track of all of our discoveries, filter our discoveries, interact with the brokers for other discoveries, DESI spectroscopic data, LSST data, annotate, if you have theorists working in your group and they say, I think it's this or that or the other, it keeps track of all of that. So this gets to the heart of many of the things that I find important. The ZTF uniform depth survey, after the references were done in the first few months, December through February, sort of plowed along with a high cadence wide field 3 filter survey. And weekly, they were getting down to 20-second magnitude. And whenever we found something, we'd go back and do force photometry on the entire history of stacked data previously, just to see if there were things sort of below the 5 sigma level, which is our initial detection. And here you can see some examples. This is a TDE that was found way below the nominal detection threshold by stacking the data. One of the things that we're interested in doing, at least from the cosmology side of things, is building up large samples to do peculiar velocity studies. And here we would do them with type 1a and type 2p supernovae, combining data from ZTF in the north and LIneA in the south. And so you'd have tens of thousands of nearby standard candles in order to calibrate the peculiar velocities. And when combined with redshift space distortions from BAO measurements, it's a really interesting way to test general relativity. There's also a big push to measure the Hubble constant, and so that can be done with standard sirens as well, which is another big push. And so wearing my DOE cosmology hat, this is sort of what we're interested in. So now the who. Now, so the group we brought together is actually a bunch of people that I know that were not playing a role in ZTF2, but were interested in extragalactic astronomy. I eventually capitulated and invited in a few people that were interested in Milky Way science. But the primary focus is on nearby supernova and multi-messenger astrophysics. The executive committee, the folks that are pulling things together, the funding and the instruments and the CCDs and the compute are Berkeley Lab in Princeton, Northwestern in Tel Aviv, Yale, and Portsmouth University. And we hope Princeton is joining us soon. And then we have a much larger collection of European institutions who are interested in the stream to do their own science. And you can see the list there. So this is sort of what our tentative view of what we're going to put together over the coming year. A 20 square degree field of view with 2 fixed filters, G and Z. The reason being here is it's optimal for the gravitational wave follow-up as well as for the supernova follow-up. Maybe something like 45-second exposure with 15 seconds for read and slew. Fixed filters, of course, so you just shuffle up the 10 square degrees to move from G to Z. G band will be about 21st magnitude in that time, half magnitude fainter during dark time, a half magnitude brighter during full moon. Z band is going to be 20th magnitude anytime we open. Covers something like 4 square degrees a night. You could do that every night if you just hit it once in G and Z. If you want to hit it twice a night in both filters, that'd be 2,000 square degrees. You could do every other night 8,000 square degrees, something like that, but pointing up. We would do this during the Chilean summertime, so sort of August through to May. And it'd be an extragalactic survey. And then during the winter, where we can't maintain a great cadence, we would focus on doing galactic astronomy, where the nights are long, but maybe you're getting 1 night out of 3 where you can open. 90% of the time, it'll be in the survey mode. 10% of the time, we've reserved for targeted opportunities. Very important here is that we will have real-time public data, the data streams, and shortly thereafter, the imaging. So final slide here, the status. We just received tentative approval from ESO to move forward. So we're starting to pull together our resources and do our budgets and test CCDs and go from there. Our overall science goal is really to fill in the Rubin Observatory's LSST cadence to maximize the science. And if you combine with HatPy, you're basically maximizing the science, you know, from the brightest objects to the faintest objects we can do a survey on. A good focus on peculiar velocity and standard sirens, but a ton of great transient physics on young events that'll be available. And our R&D plan, we have some engineering to do, but it's not much. And the amazing thing is we've done this 3 times before. And to state why it's realistic to achieve this in a year, DESI needed to do a 5,000 square degree survey of the northern sky in Z-band to complement the data that they received in GNR for the Bach telescope, that they were able to do all in one with deck cam below a deck of +30. So that's as far north as deck cam could go. It did a GRZ survey for DESI target selection, but they needed a Z-band survey. They basically yanked out the old camera, mosaic camera from the Kitt Peak Observatory. They refitted it with LBNL fully depleted CCDs, and they put it back on, and they had 2 years to do that and conduct the entire survey, and basically the instrument was complete in 6 months. We're basically doing the same thing here. We're taking the LIneA Quest telescope, yanking it back up to Yale, and then chopping it out the old CCDs and putting in these new CCDs, not new, they're the DES CCDs, but they're the ones that Fermilab is, science grade ones that Fermilab has on the shelf that we'll just need to retest. Pipeline work has already started. Danny Goldstein is doing that work. Sky Portal is being tested and evaluated on ZTF right now. Everybody seems to be very happy with it. It'll only be better in a year. And these projects are all funded through 2022. So that's where we're at, and I'll take any questions that you have. Thanks.
Thank you very much, Peter, for the very interesting talk. We have now time for questions. If you joined us on YouTube, you can ask your questions in the comments section, and I will redirect them to Peter. So, questions? Okay, well, Peter, I don't know if I understood everything well, but this survey from LIneA, it will have only spectroscopy, or will you also have photometry and?
So purely a photometric survey at LIneA, but right next to LIneA, well, within LIneA, we have the SOX telescope. So that will be, they will be fed to get the spectra of the events that we find photometrically. So that's sort of the big push there.
Okay.
I see a chat question. Is there any microlensing?
Yes.
So yes, there are people interested in that, and that will form, I think, how we design the cadence during the Chilean wintertime. is to concentrate on the galaxy. But of course, we're going to be observing enough of the galaxy during the summer as well. There's only so much sky out there. So yes, we have several groups that are interested in this, and we'll be streaming all of that data publicly, so anybody can just grab that data and doing it. I think the G and Z filters make it nice because microlensing, of course, is gray, and so the magnification in G and Z should be the same. I think Z-band also allows us to get after more stars in the Milky Way because of extinction by dust. And so I think we're also going to be more sensitive there than a lot of other surveys. And then once again, you can imagine coupling this data with LSST in ways in which, maybe LSST's cadence isn't the best. So maybe we focus on the shorter microlensing events. I don't know. But folding everything in together, I think we become a really good data stream in order to basically get rid of interlopers at the very least. There are a lot of variable star contaminants that we need to worry about, and I think will be very synergistic with LSST in that regard. Also, LSST won't be, just staring at the galaxy every single night for microlensing, whereas during the Chilean winter, at least, we have that opportunity. So.
Okay, well, thank you. I don't. Is there any other last question? If not, I'd like to ask you the last question.
Okay.
Well, I don't know if you already decided on the filters you will use, but for people who wants to study the solar system small objects, will there be some content? How deep are you going in magnitude?
Yeah.
For
So.
instance, to study TO or
So we thought about the solar system, and the thing is, where would we be complementary to LSST, their survey, and that's a problem in this. Well, not a problem, but they go so deep, and they're going to cover the sky in a reasonable enough way that is there any science that would be valuable that they can't do automatically. We've yet to come up with a good case that says we would be better than LSST. We would certainly entertain it. So if people have ideas, we're going to get to 21st, 20th magnitude in G and Z. So it's not optimal, right? Because the reflected sun spectrum sort of peaks in R band. So we're not as optimized as other surveys, but we certainly will find solar system objects. I just haven't seen a science case yet for why we would be interesting compared to LSST. So maybe for some very fast moving objects. That's all I could imagine. So things that make streaks, things like that.
oh, yeah, fair enough. Well, thank you, Peter. I think we will now wrap this up.
Let the
For
next
the
meeting
next
come in.
week's webinar, we will have yeah, we will have Jelko Izevich from the University of Washington talking about the legacy survey of space and time with the talk entitled "The Greatest Movie of All Time." Thank you, everyone, for attending, and a special thanks to Peter. Thank you very much. And everyone, have a great day and see you next week. Thank you.
Have a good one, everyone. Bye.